So now for something completely different. So this doesn't really relate to surveys or anything like that. I wanted to come back and take a look at something we'd seen previously. And one of our examples, we saw that when we played around with various combinations of set operations, we kind of ended up in the same place. So in particular, if we find the union of a pair of sets in one instance, and then we took its complement, everything that's outside that union, once we did that, we ended up getting the same thing that we produced when we took each set's complement, set theory, opposite deal, separately, and then formed the intersection of those two things, the overlap, what they have in common. So it feels when you write it out symbolically like this, sort of like you're kind of like distributing, that complement, but having to change the symbol in the process. And at the time, I kind of left it hanging up in the air as to whether this was a coincidence or something that ends up being true in all cases. And as it turns out, one more way we can use Venn diagrams is sort of to confirm this for us. So what we're basically going to do is kind of use a very specifically constructed Venn diagram and then take a look at what's going on. But I'm going to need to make myself some space here. All right, I'm going to try to give myself a little more board space to work with and actually cordon off my Venn diagram. Hopefully this is still readable for you. So I've got my Venn diagram, universal set A and B living inside it, the same kind of overlap deal. What I'm going to do is rather than get really technical with this or worry about specific set configurations, what I'm going to do is take each distinct region of this diagram and put a number in it. So sometimes I've used Roman numerals in the past, but then like my Roman numeral 3 and my Roman numeral 4 end up not looking all that different. So I've got to be careful with that. So I've also done things in the past where you sort of shade stuff in using different colors or directions of shading. But I think this will do the job for us pretty clearly. So I think it's good to go this route. All right. So what we're going to do is take a look at what happens for our different combinations of set operations and then see if it always ends up working out to be the same. Because now, what we've done by just sort of putting this single element into each one of these chunks of the diagram, we're not worried about how dense any one particular set's configuration is, about how many things are here versus in the overlap, or if something happens to be empty or what have you. This way, we're seeing exactly what regions we're ending up catching. So, having said that, So if we take a look at what A union B would represent on the left-hand side of that equation that was up here earlier. So remember the union, it's kind of like we just get rid of those, we wipe out the boundaries and then we kind of treat the two sets as now one object as far as the union is concerned. That gives us region 1, region 2, and region 3, right? So you technically don't need to do it with this roster format, but I think it kind of helps, reinforce what we've talked about before, and it gives us a nice way to collect things together. All right, so the union consists of 1, 2, and 3 on our picture, and then we want to take the complement of that. Remember, complement, as we've seen before, is everything that's outside this thing. So we want anything in our diagram that is not one of these guys. Well, that's just 4, right? So there's one side down. The complement of this union basically just means we want kind of this outside. If we had shaded stuff in for the union, we kind of would have colored in everything inside the circles and said the complement is the stuff we didn't color. So that's 1. All right, let's go on the other hand. So the other side said A complement's intersected with B complement, right? So, well, the complement of A is everything that's not in A. So what's outside the A circle? Well, 1 and 2 are inside, so that means 3 and 4 are outside. So those are some of the best curly braces I've done in a long time. I'm on point. Anyway, so then we'll do the same thing for B complement. So what's outside the circle for B? Well, 2 and 3 are on the inside. That leaves 1 and 4. And there we go. I messed up now when I said something. That's what I get, right? So 1 and 4 make up B complement. And then we want to form the intersection of those two guys. Well, remember the intersection is like it's the overlap. what do they have in common? What's appearing in both of these things? So, as it turns out, yeah, just 4. 3's only in A complement, 1's only in B complement, so, yeah. So we got just 4. The same thing we got down there. So again, you could do sort of a shading thing where you shade A complement like one color, like red or something. Shade B complement blue, and then whatever is purple, because red and blue are supposed to make purple, would be the complement, or the intersection of those complements. So as it turns out, yeah, this ends up sort of verifying for us that regardless of how the sets A and B are configured, these two things are always going to end up being the same. No matter what, we always end up with sort of this, on the outside, content or region, whatever you want to call it. So, as it turns out, this ends up being important enough that it gets its own name. All right, well, it gets half of its own name. It's weird. Anyway, so as it turns out, this property we just verified is one of a pair of properties that are collectively known as De Morgan's laws, named for mathematician Augustus De Morgan. He wasn't French, despite the "de" in the name. Anyway, so as it turns out, they kind of give us a way to so in a sense, as I said, distribute like a complement across one of these other set operations. So as it turns out, just like we verified, the complement of a union is the intersection of the individual complements. So yeah, we can kind of pass the complement along, but we got to flip the symbol. This U gets turned over down into the upside down U in intersection symbol. Again, you get the idea. And hopefully, not surprisingly, if we had a union on the inside and we got intersections, well, I'm not going to belabor the point. I'll leave it to you as an exercise to confirm that it does end up working out. You can repeat what we did previously. If we have an intersection inside these parentheses and we take a complement, as it turns out, again, we can distribute the complement. Distribute. I'm always wary of saying that in case it's not really distributing, but you get the idea. But then that symbol again flips. The intersection in here becomes a union, of the individual complements. So those are De Morgan's laws. As it turns out, we're going to see De Morgan's laws again in the next chapter in a seemingly different context, but the same sort of principle is going to apply. So I like bringing it up early, so when it ends up showing up again in the next chapter, you kind of got a little basis for why this stuff is ending up working out. All right, so that's set theory. That's half of what we need to talk about in this chapter 2, but the first chapter of content we're talking about. So next time, brace yourself for this. This may feel weird for a college class, but next time we're going to count.